This is part 6 of the tutorial about type classes. So finally, having formulated the laws of type classes in terms of monad algebras and comonad coalgebras, here's what it gives us. It gives us a technique to show that certain type class derivation patterns will work in the same way for all type classes and for all sets of laws. We begin with algebraic type classes. So suppose that we have found somehow the monad M that encapsulates the law. So this difficulty that I was talking about in the previous tutorial, about difficulty of finding this monad M, that is because the choice of this monad must encapsulate the full complexity of the laws of this type class together with all the complexity of its operations. So somehow this must be chosen into a single monad M that is magically able to enforce all of this, both the operations, induce the operations, and enforce the laws through its monad algebra laws. And well, but suppose we found such M, and we know it exists in some kind of theoretical sense because it's the free instance constructor of the type class, and free instance constructors exist for all algebraic type classes. Again, this is perhaps something that might be difficult to find for a specific type class, but in many cases we have found them. So suppose that this M is given, then what do we need to prove in order to prove the type class derivation patterns? So let me go back to the initial slides where I showed those derivation patterns. So for the algebraic type classes, we have these patterns. So if we have a type class C, then the unit type is an instance of C, and then if we have two types A and B that have instances, then we also have the pair instance. If you have instance C, A, then there is an instance for a function R to A where R is a fixed type. And finally, the fixed type. Now, the free instance here is something that we assume is given. And then we are going to prove that all of these four instance constructions satisfy the law. So how do we do that? What actually needs to be proved is that, say, the type T that is set to the unit type is an M-monad algebra. That's all you actually have to prove. You need to present a function of type MT to T and show that its two laws hold, the identity law and the composition law of the monad algebra, which is something I showed in one of the previous slides, these two laws. So the monad M is given, its methods are known, you have the code for them, you just need to check that this code is a function that is always equal to that function. So, well, this is very simple because the function of type M unit to unit is just a constant function returning unit, and then a constant function returning unit is going to satisfy all those equations because the result is always going to be just unit. The second case is, let's take this one. If T is an M-monad algebra, then this, for any fixed type R, is also an M-monad algebra. So I will show that on the next slide in some more detail. And then you have to prove that if A and B are two M-monad algebras, then so is the pair AB. So you have to find the function M of AB going to AB and show that the laws hold for it, for that function. Finally, if F is a functor such that Ft is always an M-monad algebra whenever T is 1, then any fixed point of f is also an M-monad algebra. So you need to, again, this property means you have a function from M-monad algebra T structure map to M-monad algebra Ft structure map. So from Mt to T to f of Mt to M of Ft to Ft. So that is what you need to show. And the laws. Now, it's much easier to prove the laws when formulated in this way, because then you just manipulate the methods of a monad in general. You don't have to worry about specific laws of a specific type class. So for any monad, this is going to be true. So here's an example how you prove this for the function type. I'm going to prove just one law because I'm not going to spend so much time. It's all written out in my book, all the step-by-step proof for each of these cases. So if you want to learn the techniques about that are necessary to prove such laws, then read the book, and you will after that you will learn the technique. So here's how it works for the type R to T. So we assume that we have a function mt of this type, and it is a given M-monad algebra which already satisfies its laws. And then we need to define this function. Let's define it. In Haskell, we define it like this. It's pretty simple. Similar to what we did in the previous part of the tutorial with functor algebras. But now we need to prove that this function, mu, also satisfies the laws of the monad algebra. So for example, the identity law, it says that composition of this mu with pure is an identity function. So if we apply this to some f of this type, and then we get, again, the same function of this type. So we apply that to some x of type R, and we should get fx as a result. So how do we derive that? So we write it out in the syntax. So this is mu applied to pure f and applied then to x. So then we substitute the definition of what mu is when applied to some arguments. So that is this, where you substitute, instead of the arguments, you substitute those things, and you get that. And then you look at the properties of pure. Fmap applied to pure by naturality is equal to pure of this function applied here. So then this is equal to pure of fx. And now this is the expression we have. This is just the identity law of mt. So it's mt applied to pure of something, and it is equal to that something, because we assume that mt already satisfies the M-monad algebra laws. And so now we have also shown that mu satisfies it. And similarly, we prove that the composition law also holds for mu. Now it's a significantly longer derivation. You need to use other naturality laws. You need to use the functor composition laws. You need to use also the composition law of mt. And I have done it in my book, and I'm not going to show it here because it's just longer. But it is conceptually exactly the same thing, where we want to show that some equation holds for some functions for which we have code. So we need to simplify that code using the laws that we know, and that requires learning the technique of knowing what those laws are and where you can apply them, such as naturality laws, composition laws, and so on. So the result is that we have proved in general that these algebraic type class derivation patterns, such as the pair, the function, the recursive type, they always satisfy the law of any type class, the laws, any laws that you might have of any algebraic type class that you might have. So once and for all, for example, the pair constructor, we have proved that pair of two monoids is a monoid, the pair of two semigroups is a semigroup, the pair of two pointed functors is a pointed functor, the pair of two functors is a functor, the pair of two contravariant functors is a contravariant functor, the pair of two applicative functors is an applicative functor, the pair of two filterable functors is a filterable functor, the pair of two monads is a monad, and so on and so on and so on. At once, we have proved that all of that is true. Or if you have a fixed type t, then a fixed type r, then a function from r to a functor is again a functor, function from r to a monad is again a monad, function from r to a filterable is again a filterable, function from r to a contravariant functor is again a contravariant functor, function from r to a monoid is a monoid. We have proved all of this at once, together with the proof of all laws holding for all type classes that have algebraic type signatures. So that is the power of this approach. The coalgebraic derivation patterns are exactly the same in spirit. They just use a comonad coalgebra instead of monad algebra. That's all. So different laws you need to go through and different constructions. So all these constructions, you just go through them, you write down the laws, and line by line transform expressions, and very soon you're done. So this actually concludes my tutorial on the type classes. Let me summarize what I have talked about. Most type classes that programmers are using are either algebraic or coalgebraic, depending on the type signatures of the methods. And for algebraic and for coalgebraic type classes, there are separate derivation combinators or derivation patterns for which you can implement as a library the combinator functions. And those combinator functions are guaranteed to produce new type class instances that obey all the laws. And you can prove in advance for all type classes, for all possible laws, that this is so. The price, however, is that you need to derive the free or co-free type class instance constructors. You need to derive them for each type class separately. There is no recipe that you can use if you have a type class with laws. Then you need to formulate those laws via monad algebras or comonad coalgebras, but there's no recipe to find that suitable monad or suitable comonad that you could just plug into some algorithm. Doesn't seem to be such an algorithm. I give examples in my book where I take a monoid and I remove some of its laws, and I see, let's say, I have a monoid that has only the left identity law, but not the right identity law, but it does have associativity law also. What monad corresponds to that? And I derive that with some work, but it's every time need to derive a new monad by hand, by trial and error, and then prove that this is correct. It's not very easy to do that, and in some cases nobody knows maybe how to do that. However, the good thing is that we have a very general picture of type classes, starting from the point of view of type theory and category theory, where we were able to talk about very general properties of those type classes. As I would remind you that algebraic type class with no laws is just the category of functor algebras, and algebraic type class with laws is just a category of monad algebras, and for a particular monad, of course, and for a particular functor. A coalgebraic type class without laws is the category of functor coalgebras. The coalgebraic type class with laws is the category of comonad coalgebras with a specific, correctly chosen comonad. That view allows you to look at type classes kind of in a very abstract way and talk about properties that are common to all type classes. This is the power of category theory. Now, of course, do you actually need such power in code when you're coding? Do you need to talk about properties that are common to all type classes? What are those properties that could be common between functors, monoids, and contravariant functors, and monads, and applicative functors, and something else? What are such properties that are common between them? So here I have a list of those properties, and I proved all of them in general. Now, in practical programming, you might not want to use that necessarily. Type class derivation is usually done manually and not through libraries that automatically derive you a type class. But some programming languages provide such libraries, and it can be done. And so this theory provides you a foundation for making such a library and making sure that all the laws hold. This concludes my tutorial.